Hey tubers, Q here. This video is about LED RGB track lighting, like you see here. I couldn't find any good documentation about this stuff when I was trying to set up my build. So I went ahead and put it all together, figured out how it worked, hacked it, and now I'm going to show you how it works. RGB track lighting consists of the following components here. You get your RGB LEDs, which come in big spools like this. You'll need a power supply. In this case, this is a 24 volt, 15 amp DC power supply. I just bought it off of Amazon. This is a controller, which sets up combinations and patterns of color, or you can set the color. This is the part that I was really interested in hacking and making my own. And then you have RGB amplifiers. And what these do is they amplify the signal from the controller in combination with the power supply to make a nice fat output. I ordered a whole grip of this stuff from Amazon and eBay, and each one of these spools are 10 meters, 24 volts. Each one of them has 600 sets of LEDs in each strip, and each one of these requires about 5 amps. And so I've set up about 40 meters in my house. And so I have 2 of these power supplies powering those 40 meters, and I'll show you that in a second. Alright, I'm up on here on the second floor, and I want to show you my actual electrical setup that I have for now. It's fairly crude. I want to make this a lot cleaner, but I can at least point out how it's connected. The controller signal comes in on this side into this first RGB amplifier. And the RGB amplifier has an output that goes to one bank of LEDs, and it's also got power coming in from this power supply. And that input signal is split, and it can go to a second bank up here into this other RGB amplifier, also being powered by its own power supply, and it's got its own output to a different bank. And so those 2 banks combined give me all of the lighting I need for everything that I have set up right now. So all this stuff over here, all these lights, all these lights. This is the controller that came with one of the LED strips that I bought. And what it lets you do is set one of these colors here. If you click one of these buttons, it makes the color change to that. You can also customize colors by hitting that button and then making it more red, more green, more blue. So you can kind of set your own colors. And it also has a variety of fades and then jumps. And jumps are just like things where it switches around the color pretty fast. So, basic kind of light show sort of stuff. But I figured out right away that the fidelity that it gave you for setting the color was very low, because as you go up and down with red, there's only 16 steps of red and 16 steps of each color. So the fidelity in what you can really get is pretty low. And also on top of that, the frequency that the pulse width modulation was running at was it's 120, and I'll prove that later. And 120 frames per second sounds pretty high, but when it comes to lighting, if you look around very quickly with a sort of strobing LED, you can see little dots, and again, I'll show you that later. But this whole sort of solution wasn't quite good enough, and I wanted to just play around with it, and so I made my own PWM circuit and made my own patterns and things like that, and I'll show you that next. So this is the circuit that I ended up building. It is 2 Arduinos. The reason there's 2 Arduinos is that this particular model Arduino only supports 2 pulse width modulation channels, per device. So I attached a second one, and I talk to it through an I2C interface, just so I can get that 3rd pulse width modulation channel. So it's a little bit silly. This whole thing could be replaced with AT Mega 328M or whatever it is that has 3 pulse width modulation channels on the same board. But yeah, and then I have these 3 transistors. They amplify the pulse width modulation signal. That output goes directly to the RGB amplifiers that are upstairs. And what's cool about this is that if you remember the original controller, I measured the pulse width, like the rate that it was going, the frequency it was going, it was about 120. Probably exactly 120 hertz. And that 120 hertz would cause some level of sort of strobing. If you look around quickly enough, you'll notice some amount of strobing, just visually. And it turns out, if you believe all the latest VR research, your eyes can see around 1,000 frames per second. In sort of the right contexts with fast-moving and strobing light, you can see up to 1,000 frames per second, or maybe more. And so I went ahead and tuned this guy to run at 2,000 hertz, and it was a little bit of a compromise because instead of 16-bit, now I have to use 13-bit. But 13-bit is 8,192 values, still pretty high, and the frequency is 1,953 hertz. So it's completely, like any strobing is completely imperceptible, and I think that's what makes this cool. Plus, I think the color resolution compared to the original thing, I think is much higher as well, or at least I have much better control over it. So that was sort of the whole idea with the project, and I think it's pretty cool. This is a simple block diagram of how the wiring works. The controller has 4 outputs, an RGB and positive power. And that controller signal can be split up between as many circuits as you want. This goes into the amplifier, and then the amplifier uses the power supply, and the output comes out of the amplifier as the actual LED strip here. So you can add as many of these power and amplifier sets if you wanted to extend it this way. You could just add another amplifier here. It has its own power, and then it would have its own set of LEDs. But actually the prescribed way of doing this is to daisy chain them. And I'm not doing it that way for a couple of reasons, but the most important one is that I'm actually driving the input here at 5 volts, whereas a prescribed way to do it is the controller actually outputs 24 volts, and so the input to the amplifiers are always 24 volts. And what you could do is you could daisy chain more amplifiers by actually putting it at the end of the LED strip. You still need a power here. So I'm not doing it that way, partially because of the geometry of my setup upstairs, but also because I'm driving it at 5 volts here, and I'm going to explain why here in a little bit, why I'm doing that. This is very roughly what the brightness graph looks like for any given input on the PWM. So on the bottom axis here, this is the pulse width modulation duty cycle, and I drew a little square wave right here to sort of reinforce that this is a 50% duty cycle right in the middle, and then the y-axis is brightness. And out of the box, as soon as I started playing this stuff, I noticed that the brightness curve was sort of very heavily biased like this in this exponential way, and there was even some missing stuff down here where below a certain value, there just wouldn't be any light at all, and then it would sort of all of a sudden turn on. And this kind of section in here was kind of the most problematic because it just seemed like it would be completely off, and then there'd be, increase it by 1 or 2, and then it would actually seem like it was at 20 or 30% brightness already. So I fixed this a few different ways. The first was I just changed the input voltage on the controllers. So, like I was saying before, the prescribed way to do it is with these 24 volt input and controllers. But what I discovered was I could bump down the voltage, and I could start to smooth this out quite a bit actually. And so I ended up with a curve that was maybe like that or something, just with the voltage stuff. And that was getting pretty close to linear. And then for the rest of it, I just use a mathematical exponential function to just flatten it out as well as I can. And I don't think it's perfectly linear, but it's pretty close. It's definitely a lot better than how it worked out of the box. And I've just shown this in red here, but all three of the colors had that same basic problem, but with different sort of values for the bottom. And another thing I ended up doing with the green, because the green had a different problem, which was it was just way brighter than everything else. And if you know anything about how your eye works, it's because your eye is much more sensitive to green light. And so I set a different top value for green, just to give it a different top value to kind of match it with all the other colors. One other interesting thing about these RGB lights is, so one of my expectations was that I was going to be able to create this kind of nice, soft, warm lighting, or at least, you know, white lighting by combining all three colors. And when you look at the LEDs, when you have them mixed together, it does actually appear white. But if you look around the room, and I'll show you here that in a second, if you look around the room, you'll notice that things look kind of weird. And after some thought, I decided that this was because these LEDs, each individual color of LED, actually only illuminates a pretty narrow part of the color spectrum. And in particular, the blue, it seems very, very kind of spiky, and it's almost kind of ultraviolet. There's some stuff that I have here that fluoresces in this light. The green, I think, is a little bit wider, and the red is kind of narrow as well. So if you wanted to, you know, kind of a complete nice white light, you know, the ideal would be just a straight line here. But instead what you have is, yeah, you've got that. And so all this stuff is just missing. All this light's not being produced. And you can tell when you look around the room. So I wasn't able to achieve this kind of like cool, warm lighting effect that I really want. It's still pretty cool. I can still work with it, but there'll just be certain things that look strange, depending on where they are in the color spectrum. Some things will appear too dark because there's just not any light being produced at those wavelengths. So code-wise, this is just an Arduino project for the most part. I'm using wire.h because I need to use the I2C interface to talk to the second Arduino to send it just a value to set its pulse width modulation at. At the top here I have some calibration values, which I had talked about before. PWM top is telling the pulse width modulation timer, timer 1 and timer 2, to use 8192 as the top value instead of the 2 to the 16th power, and that's how I get the higher frequency, and I'll talk about that a little bit more in a second. Calibrating top red, top green, top blue. So I explained that the green was way too bright, so I set the top green value to its maximum minus 3,750. So it's almost half as bright as the other colors. When I tell green to be maximum brightness, it's only about half as bright as the other colors. But it still evens out. It still looks like the same luminosity, at least to my eyes. Bottom red, green, and blue, those are the values I showed you on the graph, where below these values you just didn't see any color at all. This part right here, I think, is what we're talking about. The pulse width modulation with the sort of the default Arduino library is fairly limited. It doesn't really explain how to kind of get the most out of pulse width modulation. It just tells you you can turn it on and off, and you can set values. And I think it's defaulted to 8-bit or something like that, or maybe 10-bit. I can't quite remember. But the thing is, if you go into the actual data sheet for these chips, you can unlock a whole lot of stuff. What I'm using here is what's called fast PWM. And it's just a matter of configuring these things by setting these values. And I won't go into that because it's sort of out of the scope of this video. But if you understand this stuff, you can go through and you can set different kinds of pulse width modulation. You can choose 8-bit, 9-bit, 10-bit, fast PWM, or phase correct PWM. And the default Arduino stuff is all phase correct. And they do that because servos are sensitive to phase. But other things like what I'm trying to do, I'm more interested in speed, so I choose fast pulse width modulation. And I also set the top value to something other than the default. So this is normally a 16-bit timer, and the thing only runs at 16 megahertz. And so if you're running 16 megahertz and it's a 16-bit timer, then I'll just do the math real quick. "16 megahertz divided by 65532, that's 244 hertz. And if you use phase correct pulse width modulation, that'd only be 120 hertz. And 240 hertz is just not quite fast enough for what we're trying to do, because like I said, as you move your eyes around, if you dart your eyes around very quickly, you'll see strobing, and the whole thing doesn't look smooth, basically. So the most correct way to measure the frequency of these controllers is to use an oscilloscope, but I thought it might be interesting to use photography as a sort of primitive oscilloscope, and it turns out it actually works pretty darn well. This is a picture I took of the demo controller, the controller that came with the LED strip. And what I did here was I took a picture at 1/10 of a second exposure. Okay, so that's 100 milliseconds. And then what I did was I just swept the camera vertically. I took the picture as I was moving the camera in a vertical way. I was swinging it around. And as it turns out, you can actually see the pulse width modulation signal quite clearly here. This is almost as good as an oscilloscope. And so on 100 milliseconds, you can actually see the pulse width modulation signal coming down here. And you can count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And I think that this 13th one you could easily absorb into this first one here. So that gives us 12 cycles. And that makes sense because that gives us 120 hertz, which is a fairly expected value for a piece of equipment like this. So, of course, I decided to improve on that and jacked it up to 2,000 hertz. And the way I did that was through the pulse width modulation on the Arduino. So I took this picture, and this one is at 1/100th of a second. So I wasn't even able to really capture the same kind of information with the same exposure. I had to actually change the exposure speed in order to get a meaningful sort of graph to look at. But this is the picture at 1/100th of a second of the final setup. And if you count them now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So 19, but this time times 100 because it's a 100th exposure. That gives us about 1900 hertz. And for extra coolness, I just wanted to make sure that that actually added up. And so if you take 16 megahertz and you divide it by 8,192, which is my pulse width modulation top value, you get 1,950. So I got 1,900 approximately here, 1,950 just with the sort of from the technical documentation. So I thought that was a pretty neat way to look at it, and it's interesting to know that you can use a camera as a sort of primitive oscilloscope. Pretty cool.